Okay, welcome back to the lecture. We have seen this figure earlier. What this diagram tells us, we talk about ring. Ring may have unity, may not have. Ring may be commutative, may not be. What are the actually compulsory things for multiplication? Multiplication must be binary and associative. And one more thing, multiplication should distribute over addition. These are the only things, these are the only compulsions on multiplication. Now see, if the multiplication has unity in a particular ring, we call it as a ring with unity. It is not necessary that every ring with unity must be commutative. It is not so. So some rings may be commutative, and maybe there are some rings which are commutative plus they have unity. So this kind of thing you're watching in this diagram. Now, what is an integral domain? Last time we have seen an integral domain. It's a commutative ring with unity where there are no zero divisors. Yes, where there are no zero divisors. So that is an integral domain. And going bit ahead, we have shown that every integral domain is nothing but a field. What is a field? Field is a commutative ring with unity where every non-zero element has an inverse. Means every non-zero element is a unit element. This we have seen. And last time we have shown that every field is an integral domain. So I would like to go back to the statement again. We have shown that every field is an integral domain. So when I say it's a field, I assure that it's a commutative ring with unity and every non-zero element is invertible. So if I'm saying A is non-zero, will mean that 1 upon A exists. So I think we have it here. We have it here. And now what we want to show, it is an integral domain. We take the help of the fact that whenever a ring is without zero divisors, means there are no zero divisors, in that case cancellation laws hold. So this is the fact yesterday we have seen. So here we started with A into B equal to 0. What we want to show, there are no zero divisors, and we assume that A is non-zero. Because A is non-zero, it must be invertible because it's a field. So 1 by A exists. By 1 by A, I multiply to this equation on both sides, on the left. So 1 by A multiplied to AB will be equal to 1 by A multiplied to 0. If we multiply by any number to 0, the answer is a 0. So we got a 0 here. And on the left side, we used associativity for multiplication. So we got 1 by A times A. And we know 1 by A times A, they are themselves inverses of each other. So the product is multiplicative identity, that is 1. 1 into B will be B. So directly we got B is 0. So whenever the product is 0 and I know fixed that A is non-zero, then surely B must be 0. Means what? Unless I multiply to a 0, I cannot get 0 entry. Means this particular set, I mean the ring, it does not have zero divisors. And if it does not have zero divisors, very naturally it's an integral domain. That is the definition of integral domain. So I feel you followed the fact. So this figure is a very, very important figure for us. What it indicates? Every field is an integral domain. Field is a subset of the set of integral domains. So every field is an integral domain. Okay. Now, if I put one restriction on an integral domain, that is, it has finitely many elements, then it becomes automatically a field. So now we are going to prove that every finite integral domain is a field. So what I mean by this, Finite means I can count the elements, finitely many are there. And I want to show that it's a field, means what are the requirements for me? It must be a commutative ring with unity. So in case of integral domain, it is automatically commutative ring with unity. All right. So what else I want to show? Every non-zero entry has an inverse. If I show every non-zero entry has an inverse, then it will become a field. So it's our job to show that every element has an inverse, multiplicative inverse, provided it is non-zero. Now, because I'm saying I want it to be non-zero, so very separately here you can see 0 is mentioned. 0 is additive identity, as you know. 1 is the multiplicative identity, and more elements are taken. They are numbered by 1, 2, 3 up to n. So in all, I hope all of you are watching. There are n plus 2 elements given. Do you observe?
Yes, ma'am.
Yeah. So there are n plus 2 elements, means the ring is a finite ring. So these are the all the elements of this particular finite integral domain. Now what we'll do is we'll select A from this particular ring, any A. And I say that A is non-zero because separately 0 is mentioned over here. So I'm taking A to be non-zero. I want to show that there is an inverse present in the same ring, which will play the role of inverse of A. By inverse of A, what I mean is A into that inverse should be equal to 1. So we want to show, we need to show that there is B in the ring, so that A into B will be 1. So what we'll do is, this many entries are there. So let us multiply all those entries by A. So what will happen? I multiply 0 by A is a 0. 1 by A, I'll get A itself. Then I multiply A1 by A, I get AA1. I multiply next entry by A, so I get AA2, and so on. And this AN, did you get n plus 2 entries back? Are these n plus 2 number of entries? I hope you can count. AA1 is my first entry, AA2 is my second entry, AAN is my nth entry, and these remaining 2 entries, I got n plus 2 entries. Are you satisfied? Yes. So you got n plus 2 entries back. But you know your operation is a binary operation because it's a ring. So you got back your D here. This is your D. What was your earlier D? It contained 0, 1, A1, A2 up to N. And now you are getting 0, A, AA1, AA2, and so on up to AAN. So what is going to happen? I got n plus 2 entries, no doubt. But there must be multiplicative identity present because you are saying that the operation is a binary operation. So either 0 must be 1, but it is a ring with non-zero unity. So 0 is a separate identity, additive identity. A itself, if it is 1, it may be, or AA1 will be 1, or AA2 will be 1, or AAN will be 1. So this may happen. So just we want to see which of them they are equal. So what we'll do is, let us equate some A times AI to A times AJ. A times AI is equal to A times AJ. So if this happens, are these all elements distinct? This is our claim. All the elements are distinct. Otherwise, I cannot say n plus 2 entries. So what we'll do is, This is an integral domain, you know. And in an integral domain, there are no zero divisors, means the cancellation laws hold. So A can be cancelled. And if you can cancel A, what it means, AI is equal to AJ. So AAI equal to AAJ implies, what this implies? AI and AJ are equal. AI and AJ are not distinct, they are one and the same. This is what is the meaning. I hope all of you are following this. So what happened? These are n plus 2 entries. Means I got my D back over here. This was my first assertion that I have got my ring back. Means somewhere I'll be getting one. Either 0 will be 1, but we are saying it is a non-zero unity. So 0 cannot be 1. Okay. Maybe A is itself 1. This may happen. Or A into A1 is 1. Maybe this is true. Or maybe A into A2 is 1. So either of them has to be 1. And if I say A is 1, then 1 itself is identity element. So its inverse is 1 itself. I hope all of you know this. Inverse of 1 is 1 itself. Okay. If this is not true, then I may go to A into A1 is equal to 1. What this tells you, if A into A1 is 1, means A1 is the inverse of A. If this is also not true, then I will go to next. A82 might be 1. If A82 is 1, will mean that A2 is the inverse of A, and so on. So somewhere you have to find out a multiplicative inverse. Why for? Because you need to get back your set. Your set contained 0, A, A1, A2, up to AN. So you have to get back your set. And when you'll get back your set? When the product happens to be 1 somewhere. So every element, every non-zero element must be invertible here. Have you followed? Okay. Okay, doesn't matter. Doesn't matter. I would like to once again go for the same theorem. Okay. So let me deal with Z5. This is more preferable for me. Z5. You know very well 0, 1, 2, 3, and 4 are the only entries in Z5. You know every non-zero entry is invertible. So all of you know that this is nothing but a field. Is it? Is Z5 a field? What are the requirements for a field? Okay. All of you are watching the multiplication table. So let us start. How will be our multiplication table? It is in Z5, never forget. Okay. If I multiply by 0, all the entries become 0. So let me write all zeros here. Vertically also, these are all zeros. I hope you all agree. Now, all of you know if I multiply by 1, the entry remains the same. Even vertically, we will get the same. Okay. Now I would like to change the color of 1 because it is multiplicative identity. So let me change the color. I hope all of you are watching here. Okay. Now I proceed. I multiply by 2. 2 2s is 4. 2 3s is
1.
1. And 2 4s are?
3.
Yes, it is so. So because 1 is the identity, let me again change the color to green. Okay. Now I move ahead. Let me multiply by 3 to 2. 3 2s are?
1.
Yes, again I got 1. 3 4s are, sorry, 3 3s are is there. Come on.
4.
Yes, very good. And 3 4s are?
2.
Yes,
Same.
it is true. Yes. Now let me multiply by 4. 4 2s are?
3.
Yes, that's it. 4 3s are?
2. 2.
And 4 4s are?
1.
Yes. So let me change the colors of 1. As you know, I'm just changing colors of 1. Okay. And here also. So what do you observe here? In every non-zero row, I have got the answer to be 1. Do you agree? In every non-zero row, you find the answer is 1. Means 1 is invertible. Inverse of 1 is 1. Okay, I would like to show by the same color over here. Inverse of 1 is 1. Now I go for 2. What is the inverse of 2 you find? 2 what's the 1? 2 what's the 1? 2 what's the 1?
1.
2 3 is a 1. Okay. So
Yes.
2 has inverse as 3. And reverse way, 3 also has inverse of 2. And what about 4? 4 is the inverse of itself. 4 4 is 1. So every non-zero element is invertible. Have you watched this?
Yes.
Yeah, so Z5 is a field. And this is what we are insisting, that if it has finitely many entries, then the integral domain will be itself a field. So you can say this is an integral domain. Yesterday only we talked about. Whenever we talk about ZP, if P is prime, then it is an integral domain. So Z5 is an integral domain. Now what you are observing, if I multiply 1, 2, 3, 4 by any element, what do you get? Just see. I multiplied 1, 2, 3, 4 by 4. What is the answer I got? This is the answer. You can watch in the table. I multiplied to 0, I got a 0. I multiplied to 1, I got a 4. Multiplied to 2, I got a 3. Multiplied to 3, I got a 2. And by multiplication to 4, I got 1. So somewhere I ought to get 1. Is it so? And if at all you get the product to be 1, we say they are inverses of each other. They are inverses of each other. Okay? I feel you are getting me. Again now, if you see for 3, if I multiply by 3 to every element, what do I get? 3 zeros are 0, 3 ones are 3, 3 twos are 1, 3 threes are 4, and 3 fours are 2. So what you observe, every time I'm getting the same set as Z5. Okay. So what is our first target? Our first target is to show whenever we multiply by A to the elements of a ring, the number of elements remains the same. Means all the elements are distinct. No two elements are same. So what we did, we suppose two elements are same. So can you say 0 is equal to A? Because you started with A is non-zero. You cannot say so. So very naturally you started from A into 1, A into A1, A into A2 and so on. Here it was quite visible that the entries are different. But because we are labeling them as A1, A2, etc., I have to prove it because I don't know their value. So we supposed two entries are equal. The entries are of this fashion, A into something. So we said A into AI is equal to A into AG. So in that case, this is an integral domain. So integral domain satisfies the cancellation laws. We cancelled A and what we got was AI is equal to AJ. Yes. So if AI is equal to AJ, then only A into AI will be equal to A into AJ. Means I'm talking about the same entry. Then and then only A into AI will be the same as A into AJ. Otherwise not. Means what? All these entries must be distinct. No two of them are same. So how many entries are there then? This is first. I hope I'm indicating here to the suffix. Then A2 and so on up to AN. So this many are N entries. Then this one is N plus 1th and 0 is ignored. So N plus 2th entry. So in all there are N plus 2 entries. All of them they are distinct. And the operation is binary. Means I'm getting back the same set. So any of these entries must be 1. So we are saying it must be in some order so that A into 1 will be 1 or A into AI is 1 for some I. Means what? A surely has a multiplicative inverse. Or in my wording, you can see what we stated. I'm getting back the same set. If the set is the same, either A will be itself 1 or A into A1 will be 1 or A into A2 will be 1 and so on. And so on. I can say A into AN will be 1. Okay. And every time I have to say or. Because no two entries are same. So I have to say or so many times. So what you observe, A1 is the inverse of A or A2 is the inverse of A or AN is the inverse of A, or if nothing happens then 1, A must be 1 and 1 is its own inverse. Got me? So what we achieved out of this? We are saying that every non-zero element has an inverse. So I would like to repeat the same thing in Hindi. यहाँ पे हमें जो सेट दिया है उसमें हम 0 अलग से बता रहे हैं, 1 अलग से बता रहे हैं और हम अलग से n एंट्रीज ले रहे हैं, A1, A2 अप टू AN. सो यहाँ पे हमें n+2 एंट्रीज दिखाई देती है. 0 एडिटिव आइडेंटिटी है, 1 मल्टीप्लिकेटिव आइडेंटिटी है और इसके अलावा हमारे पास और n एंट्रीज हैं. तो इन ऑल हमारे पास n+2 एंट्रीज हैं. हमें बताना है कि इसमें से हर नॉन जीरो एंट्री इन्वर्टिबल है. तो रैंडमली हम इसमें से कोई भी एक एंट्री चूज करते हैं. वी विल लेबल इट एज ए. अगर आपको ए से थोड़ा ये होता है, सभी A1 A2 लाइकवाइज हमने दिखाए हैं, तो हम इसको कुछ अलग लेटर से बोलेंगे. यहाँ पे बी बोल सकते हैं, तो इसको हमने बी बोल दिया. अभी बी से अगर हम मल्टीप्लाई करते हैं तो एंट्रीज क्या हो जाएगी फिर? अगर बी से मल्टीप्लाई करते हैं तो 0 इंटू बी विल गिव मी अ 0. 1 को अगर मल्टीप्लाई करते हैं बी से तो यहाँ पे बी आता है. A1 को अगर मल्टीप्लाई करते हैं तो b इंटू A1 मिलता है. then b into a2 मिलेगा and so on. Last entry will be b into an. I hope समझ में आ रहा है. अभी मल्टीप्लीकेशन इज बाइनरी. कोई भी दो एंट्रीज अगर हम मल्टीप्लाई करते हैं तो आंसर उसी सेट में आता है. मतलब ये जो मैंने लिखा है 0 b ba1 ba2 bn, these are all members of the same set. तो यहाँ पे ba1 इसी में से कोई तो भी होगा, ba2 भी इन्हीं में से कोई तो भी होगा, ban भी इन्हीं में से कोई तो भी होगा. तो पहले ये पता करवाना है कि कितनी एंट्रीज है, क्या ये अलग अलग एंट्रीज है, ये तो देखना चाहिए. तो अलग है कि नहीं है ये देखने के लिए हमने क्या किया, 0 तो अलग है सबसे. b अगर हम लेते हैं तो b के अंदर एड्रेस b इंटू 1. तो अभी क्या करेंगे, हम कोई भी दो एंट्रीज इसमें से उठा लेंगे. b इंटू ए आई बोलते हैं हम इसको, और b इंटू ए जे बोलेंगे. I एंड j आर डिफरेंट. I और j अलग अलग हैं. तो अभी हमको पता है कि ये तो इंटीग्रल डोमेन है, और इंटीग्रल डोमेन में लेफ्ट कैंसलेशन लॉ होल्ड होता है. b विल गेट कैंसिल्ड. तो क्या पता चलता है, ai इज इक्वल टू ए जे. तो अगर ai ए जे के बराबर है तभी b इंटू ए आई b इंटू ए जे के इक्वल होगा, उसके अलावा हो नहीं सकता. तो अगर ai एंड ए जे सेम है तभी उसका मल्टीपल b से सेम होगा, अदरवाइज हो नहीं सकता. दिस इज व्हाट अभी हमने देख लिया. तो कितने एंट्रीज हो गए फिर, ये अलग अलग n+2 एंट्रीज हो गए. ये तो नया सेट नहीं है, ये सेट तो वही है. इसका मतलब क्या है कि किसी ना किसी ऑर्डर में ये सभी एलिमेंट्स एक दूसरे के बराबर होंगे. सबसे ज्यादा इंपॉर्टेंट कौन होता है, मल्टीप्लिकेटिव आइडेंटिटी. तो इनमें से कोई तो भी मल्टीप्लिकेटिव आइडेंटिटी बनेगा. b इंटू 1 होगा, या b इंटू a1 1 होगा, या b इंटू a2 1 होगा. कोई तो भी 1 होगा इसमें से. अगर b इंटू a1 1 आता है तो इसका मतलब क्या हुआ, b का इनवर्स a1 है. अगर b इंटू a2 1 आता है तो इसका मतलब a2 इज इनवर्स ऑफ b, एंड सो ऑन. इसी तरीके से हम चला लेते हैं. तो कहीं ना कहीं हमको 1 मिलेगा, बिकॉज वी आर हैविंग द सेम सेट बैक इन आवर हैंड. तो कहीं तो भी हमें 1 मिलेगा, एंड श्योरली b को इनवर्स मिलेगा. पर b क्या था, b was one of the elements. b नॉन जीरो एलिमेंट था इसमें से. मतलब every non-zero element has an inverse. मतलब this set is nothing but a field. This ring is nothing but a field. Followed me? Okay. So next we go to the corollary. So if P is prime, then ZP is a field. So damn sure ZP is an integral domain, you know. And moreover, it has how many elements? P number of elements, means it is finite. And finite integral domain is always a field. So I think it is very sure, very directly we can say कि ZP contains P elements and ZP is itself an integral domain, P being prime. Therefore, ZP is a field. Followed me?
Yes, madam.
Okay, okay. So I would like to go ahead then. This part we will see later. So I think this is sufficient as far as integral domain is concerned. So for integral domain, let us stop here itself.